thank you everybody for your patience and thank you to be here. So it's a great pleasure to have Guido GERIG with us. He's on the sabbatical, working in New York, but he spent some months, in fact, in Switzerland. And we have the chance that he stopped by us for this presentation. So Guido is a Swiss citizen from Zurich, and he graduated in electrical engineering in Zurich. And he did his postdoc also in Zurich. After his postdoc, he was graduated as assistant professor at ETH. And during this time, he moved for a traineeship in Boston, where he met Petra for the first time. And it is in Boston, in the lab of Rob Kikenis, where he developed a segmentation tool, which is based on the k-nearest neighbor. So we all had to click several times on the image to create the different class for the segmentation. So directly or indirectly, we all know Guido GERIG for his medics software. So after that, in 1998, he moved to the US in Chapel Hill, starting in pediatric imaging analysis. It's really where he started to be interested in the dynamic analysis of the images. In 2006, he moved to Salt Lake City in Utah as a full professor, and we met during ISMRM meeting in 2012. And some of us were at this ISMRM meeting at this time. And finally, in 2015, until now, he moved to New York University, where he's still working nowadays. So GERIG make really a pioneer work in image segmentation, and now he will work on more longitudinal analysis close to clinical environment and clinical needs. So GERIG, it's your turn. I don't know if you want to have this microphone or this one.
This works. Okay, thank you very much, Francois, for this introduction, and thank you for Petra, both of us inviting me. It's really a pleasure to be here after a very long time, I don't know, 10, 15 years since I have been here last time. Okay, so yeah, I talk about challenges and opportunities. We see that also with this setup of video equipment. It's always a challenge, so it's same in our university. So the image that you see is actually an individual brain, white matter of a child. It's discrete scans taken at 3 intervals and then interpolated by a geodesic registration, but I will talk a little bit more about that. So spatiotemporal modeling, we have a lot of reasons why we like to do that, because whenever I talk to clinicians, this development, degeneration, intervention is always a baseline follow-up, also in imaging, even more that you would like to use more imaging over time. Short time will be like the beating heart, but long-term more is every few months scans, every year scans, as we see in Alzheimer's studies, especially also neurodevelopmental studies. So that's why I use all these terms: typical development, delayed development, catch-up, atypical, recovery. This is all what our clinicians use. And that's the motivation where we start to focus on longitudinal image analysis. Is that it's not enough just to have images at discrete time points, but can we help this type of longitudinal assessment by modeling? So we can keep that interactive. Please interrupt me if I miss something, if you want to hear something. So I really got the inspiration. First of all, I looked at the MRI book of Mary Rutherford. Actually met her also in the UK. And when I went through the pages, I thought, oh, there's really a lot going on month by month by month from birth to 2 years. I think there are several chapters, first 6 months, 1 year, 2 years, and different contrasts. So I thought, can't we do that with MRI? So this modeling of contrast. Secondly, very early in the year 2000, John Gilmore, who is the vice dean of psychiatry at UNC Chapel Hill, he was part of a consortium at NIH to write the white paper. Why should you support developmental studies? So I liked it very much. I mean, I drew a lot of my thoughts. So even when I write an introduction to a paper from this white paper, finally, who led to this clinical studies where they wanted to have longitudinal scans over time and actually fund this. So in our studies in my lab, not only at NYU, but also previous labs in North Carolina, Utah, we are working on a very large autism study. Now it's more than 15 years back, over 4 cycles of NIH funding. We had a drug addiction study, we still have it at UNC. So children exposed to drugs via their drug-addicted mothers. Huntington's, it's not child, it's also a kind of a developmental study with University of Iowa. Early brain development with John Gilmore, where we have neonates followed, many of them up into 8 to 10 years of age, even including a twin study. So that was the first study that I worked on with John Gilmore. Then fetal to neonatal, with Mariah Thomason, who moved to NYU 4 years ago. And then I have some other studies like eye retinal studies, progression of glaucoma, and also age-related macular degeneration. But you see, it's not just about, although I really like the early development, brain development very much, but this longitudinal exists everywhere where you do imaging in several clinical studies over large range of projects. So the whole paradigm would be if you have a kind of a range of disease, whatever you assess as a disease or pathology and time, most cross-sectional studies, they just use a window over time. Just use maybe adults or use subjects between 10 and 15 years. And then you do a cross-sectional analysis, getting p-values and say these groups differ. And in these studies, we often see that the variability over the study is much higher over the subjects than the effect size. So the paradigm, I mean, I borrowed these slides from Marco Lorenzi, who was at INRIA, Sophia Antipolis. We really want to look at the trajectory of change. So spatio-temporal trajectory getting from image data. So I have several subsections in today's talk, but I can stop at any time. I think I don't want to run over, but several of them are image analysis methodologies driven by clinical studies, but not only usable for a single study, but maybe over a range of data types or study types. And then I want to present some results from the autism study, the image brain imaging study from UNC, which is a US-wide multi-center study. A little bit about brain maturation, where we use brain contrast, not fMRI, not segmented MRI, but only the contrast of MRI to say, don't throw it away. And then a little bit about the Downs infant study. To my knowledge, it's the first large-scale early development study of Down syndrome. Okay, let's start with normative models. I mean, we all know that from growth curves of babies. I mean, we can look up what percentile is my baby or what percentile do we have for all sort of weight, shape of something or size. The question is now, can we do the same with images? Not just a scalar variable. And that led to the Atlas building. Those of you who work in image analysis, they all know about this template building. I mean, there's still a topic that we all work on and try to prove. Template building would be you take a population of images, as you see on the left side, like to know what is the middle image, the mean, or whatever we mean by mean of an image. There was 2004, there were two developments, one by Sarang Joshi, my colleague at Utah, and then Brian Evans, Jim G, who developed this ANTS package, which at least most groups use, including us. Actually, you feed in images and you have to tune some parameters and you get the template back. So the image that represents the Frechet mean, so it's not the linear mean. It's kind of a new concept because the old concept was to take a typical subject and register all the images to the subject. That's done before, but that's highly biased because it depends which subject you take because it's not centered. So you see that in the upper image here. Here we calculate the image in an iterative way based on actually the mean of the images by nonlinear deformations. So this can be extended to longitudinal. It's relatively straightforward. I mean, it took them some time to develop it because now you build an atlas based on subjects that have different ages, but then the age difference to the time point that you want to analyze is de-weighted. It's like a Gaussian function. You see, the further away the age of your image, the subject, the more you de-weight. So you get kind of a mean, but if you do that over time, you get, like here, an atlas. Here we have adult brains from 20 to 80. So you see, you do templates in an iterative way, going through all the age categories and just weigh the neighborhood in age images to get these atlases. I would say we are not the first ones and we are not the only ones who did such type of developments. There are other groups, especially also at Imperial, UCL, and other groups as well, that created this kind of software for template building. Now, in the age of learning-based methods, left we have the ANTS. This is Brian Evans and Jim G's group's work. I mean, it's really available. I know it's really used in most clinical settings where you need to develop a template. But new was the kind of deep learning-based, the learning-based framework. You feed in images, can you synthesize the average image? And one software that is known is the voxel morph by Adrian Dalka from MIT Harvard, which we started to look at. It's kind of a learning-based GAN network, which kind of was a new way to look at it, because ANTS takes very long computation time. So if I come with 200 full 3D MRI images, I have to take for very long to actually calculate the template and use mostly high performance computing sources to do that. If you have a learning-based, learning takes a lot of time, but then the image, the generation of the image is immediate. It's like a fraction of a second because it's synthesized. And okay, now there is another component that Adrian brought in, which I liked very much. It's actually the covariance. Because in our lab, they always said, ask a lab, can we have a typical female child template at the age of 10 months? Can we have a typical male subject template at the age of 12 months? So it was all subcategories, and of course you don't have enough data to do that. This learning-based was inspired by computer vision. There's a lifespan age database, 70,000 portraits. And the categories are ages 0 to 70, and the conditions were very simple. This is a computer vision task. It's not a clinical task, as you see. They have male, female, age, and then sunglasses or glasses. So that's just for fun. So what can you do with these 70,000 images with these categories? Age, female, male, sunglasses. And if you apply these frameworks, this is actually applying our software, which was kind of the next generation of Adrian Dalkas together with his group. You see here we can synthesize babies to 70 years for female, male, female plus glasses, female plus sunglasses. So this is a kind of a game. I mean, you just go in and get the image and say, oh, looks cool. But this is actually the same as we do with MRI images. To extend this framework to 3 dimensions was kind of the work of our students together with Adrian's group. We had to work a lot on this N network. Those who work in learning-based software, they are known as non-robust, non-stable. You had to regenerate all the parameters and tune them for each new study. So important would be, we don't want to go through the network, how it actually works, but it's an attribute vector. You will see we use this attribute vector. I mean, this is just the whole framework, but this is not the deep learning talk. It's a template generation subwork, a registration, nonlinear diffeomorphic registration, and a discriminator subwork, which you feed in via, again, technique. So now we applied it to clinical studies. For example, the DHCP, it's a freely available database. Some of you probably know it. 558 postnatal MRI images, aged 20 to 44 weeks. We feed those in, and here the conditions are female, male, and age. So that's why we get the longitudinal atlas with exactly the same framework as the faces. We just say, calculate the image at age 7, 8, 9 weeks or month, and give me back the template. And it's a 3-dimensional MRI image. So we still had to do a lot for tuning and getting this framework to run. You see, linear average would be if you just average all the images and you know it doesn't work, just get the blurry image. Ants, we have here a cross section, a mid-section through the brain. And you see ants still looks very blurry. So, I mean, nothing wrong about it. We use the software. It was the first on the market. Voxel morph creates this type of structure. And you see there is a problem here. For example, the cingulum is broken into 2 parts. So there's nothing right or wrong here. We just say anatomically it's wrong. And of course, since we published that, we had to show ours is better. And this is our version of, it's sharper, the image. It comes closer to a true, or how can I say true or not in a learning-based framework, but it looks more real as an image. Or if you look at the stability over time, voxel morph to the left, we go here from 30 to 44 weeks. With voxel morph, you don't see a lot of morphometric changes. The brain is nearly stable. Probably it's too much regularized. If you look at our version, we have to sell our idea. You see there is really a lot of structural differences over time that you start to see. Structures get shifted, they get bigger, they change size and shape. Okay, here applied to our autism study. I will get to that later. Infants scanned 6 to 24 months, 3 discrete time points. And here you see the other challenge that Neil Day had to solve. It's the change of the contrast in this range of 6 months to 2 years. So we had to bring in a lot of new parts into this generative network, but you see here, this is what I also see in Mary Rutherford's book. I just say, how does a typical neonatal book look like, brain look like? What is a 6 months? What is a 12 months? And you clearly see this kind of white matter contrast change over time. Okay, we also applied it to the Huntington's disease study. I now jump to a different study because the autism study is still in progress to show differences in development. And here we just studied ventricles, caudate, pallidum, and putamen. And once you have a segmentation and the atlases, you can somehow plot the differences and do further analysis of differences between two groups. So that's more the goal. The next step, how do we use such templates for a clinical study where we have multiple groups? Sorry. So code, everything is available. That's a nice thing about today's learning-based. Everybody puts it on GitHub. Very nice documentation, paper itself and how to use it, and you can run it yourself. Okay, so that's about template building. In a similar way, two of my students, Mongwei Ren and Neil Day again, they thought about segmentation. How do we do segmentation now, and how could we extend segmentation over the longitudinal axis? So this is what we did so far. This is again images from the infant brain imaging study. We have scans around 6 months, 12 and 24, and we segment them independently. Just get the scan, put it through the pipeline, and you get this white, gray parcellation, whatever. You could use FreeSurfer or something else, but there is no correlation or something that the segmentations know about each other. It's like independent. So it's really blind to the time points. If I look at the brain, if I maybe scale the images over time, I can see it's the same brain. The structures of the surface, brain surface, are like a fingerprint. So we don't use really the information across time. Okay, so we like to embed the spatiotemporal information into the model building. As here, you have 6 months, 12 months, 24. In principle, the acquisition is independent, but it's the same child. So that's not independent. So the structures look very much alike. I mean, probably you know that too from all your early development studies. Okay, main idea is getting that into a deep learning network. How do you put this information about spatiotemporal correlation in small patches over time into the network? So again here, that's again the motivation. Sorry, I replicate that. So instead of segmentation of each time point independently, we segment the whole series at once and train the network to get the more consistent segmentation. Because we know the structure should be very similar. Unless you have pathology, that will completely fail if you have anatomical pathologies. Okay, I don't want to go very much into details. Here, I must say the same as my students sometimes say, the details are in the paper. It's again a complex network that got trained. In addition to, for the training, we know in deep learning, they would say you need a lot of training data, like hundreds of thousands of images. Here, this is a one-shot segmentation. So we use one segmentation that was done actually by manual correction of segmented images for each time point, put it into the framework, and then in the learning-based approach, we change this template. We add noise, we do deformations, we just do all the simulations, what happens to real images. So if you use a template applied to a different time points, so just not doing any longitudinal, it's kind of doomed to fail. So we cannot use a 36 month template segmentation and apply to a 6-month child image. That doesn't work. So it's just a different type of contrast and structure. So this is always magic if my students explain me all the steps that they do. It's like a 2 years of work based on a learning-based framework to put in the local patch similarity into a learning-based framework to finally get a more better consistent segmentation over time. Okay, so as I said, we feed in multiple time points for the training. We have this temporal patch similarity loss function that goes in, and yeah, the whole thing is just combined. So to my knowledge, what the students told me, they presented at the NeurIPS this year. It was kind of an early paper that shows that longitudinal consistent segmentation actually improves the accuracy, because we had to do a lot of, as you do in every learning-based paper, you have to do a lot of validation studies. But the red one, you see the large box is ours, and ours is always on top. So you have to believe it or not. So it improves the consistency of segmentations if you combine it in this framework, that you know the data comes from the same subject. Okay, application. Yeah, let me see. Yeah. So this is finally what we apply to clinical studies where we have multiple time points. And you will see later when I talk about the Downs infant study, we could only segment the Downs MRI brain images by using this spatially consistent framework. Other software that we had developed for infants didn't work. Similarly, correction of diffusion weighted images, especially in children. I just have a simplified example here. Even if you have 254 directional scans, I jump a little bit here into the domain of diffusion imaging without giving you the background of, but you have 254 directional scans that actually encode the diffusivity at each voxel in the brain for calculating the ODF, so the orientation distribution function or the orientation fiber function. And often in children, this fails because they wake up, they move. So we often had to throw away a lot of those directions. That means in an infant study with diffusion images, nearly every child had a different number of directional successful scans after quality control. In a similar way here, another PhD student of mine, Hee-Chong Kim, generated a network by simulating non-existing directional scans. So if you have scans that are missing in multiple directions, you simulate them by a machine learning based training network. I mean, you have trained it in a very large scale training session by using existing data, subsampling them, training the network. And in addition to diffusion data, we also use structural scans. We use T1 and T2 images and the baseline of diffusion images, finally to make up for the scans, directional scans that didn't make it. So yeah, there was a large-scale evaluation again before getting accepted as a paper. Here I show you the result. The reference is a kind of undersampled image, only a few directions. I cannot tell you how many. It's about 8 or 12 directions only, because the other ones were corrupted. And the generated one is to the right. So that's generating the full set of 254 scans. Yeah, different p-values. So it's a very flexible framework to save images that we otherwise would have to exclude in a clinical study. We always had to throw away data, which is we should not throw away. But we said, if you have only 12 directions, how can we calculate orientation distribution function? Even NODI, so the in vivo microstructure analysis, if you have only 10 directions, forget about NODI. And we could show, and this was the validation that the student had to do, if you have a full scan with 254, it can be different. So, I mean, it can be any number of scans. If it's subsample 79, 26, only 13, you really see that the quality goes down. Mostly you see noise. And after the correction that we do by synthesizing the scans to a full set, you see that it changes. So I just show you high quality images, but that all went through a validation because we used known data, subsampled that, so we had a ground truth, and then compared the differences. So we would just say even naughty became possible on infant data that otherwise didn't have enough high quality directions. Okay, and finally, of course, we also like to see tractography images. To the left, it's downsampled, 26 directions only. Middle is the reference, and the right is ours. So I would again say this paper is available, software is available, and it saved us a lot of data. Especially, I told my students, if you have a longitudinal study, if you miss one child, a single time point, maybe an MRI scan is only $600, but then the radiology scan, then the parents who have to fly in sometimes, so it's several thousand for one time point. But if you have a longitudinal study and if you lose a lot of data, you completely underpower your study because we really want to save data as much as possible. Okay, how are we in time? Yeah. Okay, then let me first go to the autism study. It started in 2003 by Joe Peven, a psychiatry professor at UNC Chapel Hill. And they wanted to have a large sample size. And the way how do you get them? You do a multi-center study. That was a huge challenge for us at the beginning. Each center had to use the same scanner type, the same coil, the same pulse sequences, and techs had to be trained to actually use the same pulse sequences. Sometimes, yeah, we liked a few slices more, or we did it sagitally and not coronally. So they had to do exactly the same. We had 4 scan sites, and our site, together with Chapel Hill, was the image processing site, and Alan Evans at MNI is the data coordinating center. So the study is still going on. So it started with the autism results that got published 2005 by the UNC group, that there's something with brain growth. We didn't know exactly what was going on, but they said brain growth in children later diagnosed with autism is different. And what I forgot to tell you, this is a high-risk study. So we study siblings in families who already had a child diagnosed with autism. And the rate to be again diagnosed with autism is 20 to 25%. So if you recruit 100, most likely 20 to 25 of them will show or will be diagnosed with autism. Okay, so the question is, what happens, why, when? So what is the timing of autism? So again, we applied the segmentation framework that I showed. And then the first study was over 6 years. We got 1 year extension. When does it start? What is the variability? Then we had an IBIS-2. That's nice about NIH. If the inertia is rolling, everyone who did studies in the US knows, once you're accepted as a successful research group, they like to fund you. I mean, you have to show that it works. But this is really continuation over 15 to 20 years that sometimes can happen. Then IBIS-2, we had a scanner change, which was again a challenge for us, and the new connectome sequence and not the old one that we designed ourselves. Then we followed these kids up into school age. The question was, what is the modulation by schooling on autism? In that sense, how would the cognitive assessment or a cognitive behavior of children change during the school age period? And now we are in the adolescence phase. So we now have kids that we followed up over 5, 6, 7 time points from 6 months into 13, 14, 15 years. Okay, so it's like if you have MRI images of the same child over a very large period. It's not so many studies around. These studies are not yet publicly available. They will be. NIH forces us to distribute the data because it's paid by NIH, so it should be public data. Okay, so we developed this framework. I mean, there were several groups involved at UNC. We were always part of it, but we also learned from other groups how to do segmentation, how to do shape analysis on the cortical surface and volume features, parcellation of the images. I've seen even this morning, I mean, it's all what neuroimaging groups are doing, and then classification. Now for the group, we had control subject, no history for autism. I think the prevalence rate is about 0.8%. It's below 1%, but it depends on the country and it depends on clinical services. Who diagnoses these kids? So, but it's about 1%. Then we had the high risk. So those kids with a sibling diagnosed with autism, and then the high risk diagnosed later. So we did retrospective analysis. Diagnosis can be done at the age of 2-3 years. Then we went back to the data. So we had two categories, high risk positive, high risk negative. Okay, and of course, I mean, I've seen that with your recent paper in PNAS. Immediately when the results came out, we got all these news stations in our labs. If I say our, it's really a large group of 15 different sites across the US who was working, everyone with a piece of puzzle. Brain scans detect early signs of autism. That was the storyline. So it was new. And we always had this, is it immunization? That was very strong in California, that parents refused to do immunization to their children because they get autism, or aluminum cookware. I mean, there are all this news around what could start autism. But I mean, here again, early brain development in infants at high risk for autism spectrum disorder, long before symptoms appear. So with imaging, we could show, if you look at scans at the age of 6 and 12 months and do a regression, a modeling, a prediction, then we could see that the hyperexpansion of the cortical surface, that was interesting. We had volumes and the cortical surface. Actually, that was done by Martin Steiner at UNC, cortical surface calculation. I mean, we had a positive predictive value of 81%. So from 5 children, diagnosis was right for 4, based on scanning between 6 and 12 years and then predicting. It kind of was new, because that means imaging can see something which cognitive assessment cannot yet see. I mean, the first year of development. Okay, so this paper took 2 years to publish. It always came back. We had 4 cycles. Reviewers thought that's too good to be true. Do the statistics again. They wanted to get our data, send it to biostatistics in another lab, and say, can you verify that what they do is correct? So I think they would say that's too nice result that we believe you have all properly done, or is it just depending on the analysis that you do to the data? So we used learning-based feature detection or feature detection and analysis. We thought we have everything done and finally got published, but sometimes these papers have a hard time to go through because they want to be sure that the analysis is done the way that it can be replicated. Okay, so actually there is a second paper that came out, not in 2017, on functional analysis, functional neuroimaging, same cohort, because we also have fMRI data. And this paper showed the same. Functional neuroimaging at risk, 6-month-old infants predicts diagnosis of autism. So it was interesting that the MRI study, based on anatomical features, and the fMRI study actually showed the same prediction value. Okay, so brain maturation. That was interesting. So when I looked at my students at all these scans, at 6 months, 12, 24, looked at the 6-month-old scan where we all know contrast reverses. T1 and T2 is not at the same time, so T2 lags behind. But we see every child has a little bit of different contrast, even if they have the same age. So you see here the left one, T1, T2 weighted. It's really blank. I mean, you don't see gray-white matter differentiation in this child. The other child, same age. I mean, birth from MRI scan, already you see white matter structures. We actually could calculate it. This child is about 4 weeks advanced, and maybe the other child is delayed. So that's more the question, what language do you use? But for us, it was more interesting. MRI contrast is usually not used. You use segmentation, you throw away the MRI, and you save it on a disk, but then you look only at the segmentations. But we barely use contrast because it may not be stable over different scanners. It depends on the protocols. But here we have exactly the same protocol. So what we did here is we did a segmentation of the scan, and then we looked in parcellated area, what is the statistics of the gray level distributions? So gray-white matter. So, and you can clearly see in the T1 image, blue is gray matter, gray-white, gray-white, gray-white. You see the distribution shift. That means you have increasing contrast, as you see here. And the T2 is the opposite. You see, we get darker structures in the white matter. I mean, this is what we see if we look at the movie of the scan. So we just tried to quantify that and use the distance measure. Here we use the Hellinger distance between two distributions. Give us the values normative between -1 and 1. And then we had a quantitative assessment of the contrast versus the timing. And this is now a female brain, coarsely parcellated into the major lobes. And the bluish value means early or late. Now we have a timing axis. We know what is the contrast at what time that we expect. And you clearly see the pattern means MRI contrast. I would not say maturation. Maybe it's a marker for maturation. In what way? It's surely not linear. But you see occipital to frontal very clearly. And this is what I think. You can correct me if I'm wrong, but this is what I read in all the books about maturation. Then male, female was interesting. We don't have a highly powered sample. Now we would have 10 times more, but we had only 24 females and 46 males. But now you see a difference. This is the female and the male. And dark blue means late and light blue means early. And now I tell my female students or my male students are behind. I mean, students, they're kids. So we can now calculate the MRI contrast statistically shows earlier contrast changes in female in a period where it's very hard to measure cognitive. I don't know if you do cognitive assessment between, I mean, you know much more about that between neonate and 6 months. There is not so much to test, but we can now say females are earlier than males in regard to the contrast, whatever that means. And it's 9 to 23 days, depending on, I mean, statistically, it's the mean values depending on the lobe region that you have. Okay, and downs. Few minutes left, isn't it? Pardon? Oh yeah, okay. So, longitudinal study. I told you we started Down syndrome. That was interesting. The autism study spawned off a lot of other studies. As soon as the study was successful, I mean, you probably should know that also from your studies here, you have postdocs and then they want to become assistant professors, they write the grant, and some others jump on and they get the grant on studying that and that and that. So in addition to the infant brain imaging study, the Washington University St. Louis started a Down syndrome study. It was Kelly Botteron at St. Louis. Same protocol. So NIH, we wrote the grant, Down syndrome, it got rejected. A very bad score, 3.5 or something. And then we put it into the drawer. 2 years later or 3 years later, NIH decided Down syndrome, that's what you have to do. So the group could take the study out of the drawer, not changing anything, just updating the numbers, submitting it, and it got accepted. So sometimes you're lucky to get the grant accepted. So we had still at the time when we did this study, now it's much better. We actually just downloaded a second batch after another year, but we had only 22 controls, 51 infants, Down syndrome infants. Now we have about 3 times more, and my student is currently processing the data. And here we focused on the subcortical structures. So the segmentation was done by using the temporally consistent segmentation that I talked about before. So the 3 time points segmented in a consistent way for all the subcortical structures. So very preliminary, what I show here, the plot is volume of the brain, so intracranial cavity. And we know from Down syndrome, brain size is smaller. And you see that from the plot. The yellow, blue are kind of the controls. And it's a high risk for autism study, but not diagnosed. And the red ones are the Down syndrome infants. So it's about 15% less volume in the intracranial cavity. Then we did a segmentation, this is a little bit a busy slide, of all the subcortical structures, as I showed you before, and then did a mixed effects modeling for the volumes. So more sophisticated analysis, especially shape analysis, is still ongoing on the same study. But interestingly, we see structures like the putamen and the caudate. They show the same volumes in the Down syndrome infants, even if the brain size is reduced. Especially also white gray matter is even differently reduced. The one is 12%, the other one nearly 20%. So we see some structures are the same volume as in controls, despite of the smaller brain size, and some structures really differ, like the right thalamus, left thalamus. So we see a highly nonlinear phenomena that brain growth is different, even locally. And now it's up to our clinical partners to say, can we combine such findings of whole brain volume, subcortical structures with assessments, like cognitive assessments of Down syndrome kids. So Kelly Botteron was really happy. He said, now we see something. And the nice about Down syndrome study, I mean, you see differences. There are huge differences. Not like in other mental illness studies where you need relatively large sample sizes to get kind of to a significant result. So we are still working on this study. Everybody got enthusiastic and they process more data, process the full brain. And in the same study, we have diffusion data and fMRI data. So this would be also a very nice study for other groups as soon as it's released to download and do their own analysis. There are not so many Down syndrome studies and not early development studies that we even know about. Okay, so I would say conclusions. You heard the word now 1,000 times. There's really more and more longitudinal analysis or baseline follow-up that I see in clinical studies because you want to know about the trajectory, not just the difference. You want to know, is the growth or whatever we call it, maturation, the same? But also, I mean, that's kind of a motto for our lab. Processing of longitudinal data really benefits from longitudinal analysis. We can apply conventional software, just say we don't care if there's a correlation. or causality. But this is the motivation why we developed all this software. It's still active research. I must also say we are not the only ones, and it's an exciting new way of four-dimensional image processing, which has its own challenges because there is data harmonization or other questions that we have. And what I would say is by doing the modeling, we already put statistics into the modeling process. So early days, if I say 10 years ago, we segmented the data, we gave it to the biostatisticians, they got volume data and they did nice analysis, but there was not so much interaction. Now we put the image analysis already puts in statistical modeling into the segmentation process. So our students have to know much more about mixed effects modeling or what is a proper modeling technique for linear and nonlinear growth. With that, most software that we develop is available for free. Especially, I also am the primary developer of ITK Snap tool, which I still like very much with Juszkiewicz, but we have many other tools. So especially deep learning tools become freely available via GitHub. Then I have to thank all the NIH studies that fund our research and give us and the students salaries for their PhD and postdoc times. Thank you very much. Wait a second.
You hear me? Yes. So, thank you very much. I was pretty much impressed by this contrast evolution and the difference you see in the temporal lobe between the left and right hemisphere. I don't know if you have noticed, but I think very interesting. And it's something you don't see on the frontal cortex. Yeah. And I don't know if you have a comment about that.
What do you mean the change of contrast over time? It's still, if I may say so, too simple to be true. So people would say, yeah, you cannot do that. But I think, why not? Maybe low-hanging fruit. MRI contrast tells us something because radiologists obviously use it for diagnosis. So I would just say the next step is we have to do it on a much larger scale. Now we have 400 or 600 images.
Yeah, well, I don't know if you can go back to these pictures.
So it's this one here.
Yes.
I didn't see really left, right, but maybe you're right. Okay, should we look at those here?
Next one. Okay, next.
No, next one is, I skipped this one, but.
So you see, if you go, female, in fact, more than male, but you see between this one, the left one, no, on the top. Yeah, so this one is the right one.
Let me see.
Early, and the other one, which is the left one, is later. And we have seen that in our analysis. Yeah.
So what François is pointing out, indeed, if the first is the right and the other one is the left, right? Then you would say that, the right is earlier than the left.
Yep.
And that is something we've also seen in the development of the cell size. So if you look at the deepness of the cell size, the right in the temporal lobe starts before the left, which is kind of contradictory for later on, where language, of course, defines your left shift.
Other things is,
but it's visibly changing. The right superior temporal sulcus appears before the left. And that would sort of
even
be represented in this contrast change. Yeah.
Maybe even female male is different. Yeah.
The nature is to wait until the language takes place, and it's on the left hemisphere in general?
There are 6 to 12. I mean, we feed in. It's not below 6. We didn't have baby scans in this study. So, but in principle.
No, because the left hemisphere has to keep its plasticity to allow the language to develop. We don't want the myelinization to occur too early to make sure that language. So very interesting. So I picked up this. Yeah, I've been fascinating between the left and the right differences because I've learned. I heard Landis for quite a lot of time, and he was all the time pointing out the differences between left.
Yeah, and Petra and I know that from Marjorie Lemay. She studied asymmetry of the human brain all her life at Cambridge, so in Boston.
By the way, I don't want to take the floor too long. I don't know if someone has a question to Guido.
I've got a question. It's maybe a bit of a naive question. When you fill in the data using your models for the templates and for the diffusion weighted imaging, you come up with very plausible looking data. It looks really nice. When you do further analysis of that, how do you ensure that you're really studying the brain and not studying your model?
It's a question that we hear all the time because we synthesize the data. So the whole validation could only be done within the study that we had. So in principle, you start with the full resolution of all the scans, and then you subsample, you train the network. Here we know the result should be like that, like in the NODI or in the FA values or something. If you do it with unseen data that is not seen by the learning-based framework, that's surely a legitimate question. Actually, Martin or our colleague at UNC Chapel Hill asked the same question. How can we trust your software that fills in? I would say, at your question, maybe we have to do more validation, not only within the data set we trained it, but we can even do something. We can take the B0 or the T1, T2 and synthesize a DWI image. And you would say that's magic because we don't use any diffusion. It's the same question that we have if we use a T1, T2 scan and simulated a PET scan. PET is functional and the other ones are anatomical. Obviously, it's possible using a learning-based framework. The answer that I have is we don't use it to fully synthesize scans. We use it to fill in scans where we lose too much data and say, let's at least save more data for the clinical study. Maybe if half of the directions are lost, so still half of the directions are still the ones that we measure, but not go down to 0. Because the loss of one time point is huge. So I would say maybe that's not a satisfying answer, but it's more saving data, which otherwise has to be thrown away.
It's more of a logistical aid because you have a pipeline that knows how to work with some type of data.
Yep.
And you can massage your data into the right format.
Yeah. I think there is another point which would be the benefit. We are independent. If you synthesize the data, it's lying on the sphere. Oh, I think I skipped that. Oh, I didn't show it. I mean, there's a small little picture here. In other studies, it really depends where you put the sampling on the sphere. What is the discretization of the sampling? The benefit that we have is we can choose a equidistant sampling on the sphere or same parcellation of the sphere so that all data sets we would use the same type of framework of direction scans. But again, it's a little bit of an excuse. It's like a pre-processing step that we sometimes also do to motion correction. We have the same question, yeah, fine. We synthesize the data by a translation network. Can we still trust the data? Probably that's more research to be done, how to validate that not only computer scientists are happy, but also the final end users to say, can you trust the data that you generate?
Thanks.
Okay, thank you. Dimitri first.
So thanks a lot, Guido. Fantastic talk and very diverse. So my question is about the future. So you have these models now that can link age with brain volumes. How long do you think will it take before we can link text with brain volumes? So I'm thinking stable diffusion in medical.
My students are using GPT-4 and things like that. I mean, there are studies. You can just text and say, give me a brain age 22 years with a brain tumor on the left side. Or I mean, this all exists. But for me, this is still a little bit a game thing. But I don't know. I mean, we know that from text, everybody is worried. Italy has even banned it. It's illegal to use software in Italy. I mean, if you use VPN, you can use it, nobody knows. But I'm not so sure. I mean, it took us so long, even for a longitudinal modeling of the brain development. But I'm sure with a learning-based framework, with the framework that I showed with the normative brain growth, now I can just query the data and say, give me a typical female brain age 2.5 months. Typical means an average. Female, male, or even Down syndrome. We pool all the data into one database. I cannot predict the future. We're all a little bit worried about too much progress. I think it's really all about validation and how do we use the data. So, but of course, we have to learn what is possible, and I think I don't see that what you say is not possible. So,
seems a phase transition that you kick in.
Yeah.
Thank you, Guido. Going a bit to this, big data can of course produce sort of what we think is the down brain or the normal brain, but how do we get a bit deeper with mechanistic changes that we would like to see by imaging? So you took the Down's infant brain study saying, okay, overall their brain volume is reduced. But then the neuroscientific basis of the changes in the cortical organization of the Down syndrome is actually a reduced apoptosis, so a increased cellular density in the cortex. And so even, would intuitively lead to an increase of gray matter volume. How do we address these questions with imaging?
Yeah. I mean, imaging can just offer the pulse sequence that we currently have. I don't know about apoptosis at that resolution that you would like to have it. I mean, we have structural sequences, we get more and more high resolution MRI image, we have diffusion images, we have NODI, we have all sorts of sequences. I don't know. It's probably the collaboration between clinicians who ask these questions and us as computer scientists say, do we have tools and image data that could answer your question and vice versa? I think there is even something more. You clinicians have to tell us if something doesn't make sense. Because I see a lot when we do, for example, brain cortical thickness in neonates. There are packages. I think it's not the cortical thickness, it's a subplate of the cortex that we see at neonate in MRI sequences. So I would say we need more interdisciplinary collaboration, that those who know talk to us and not just us engineers to publish something that looks good or is spectacular. So I really believe in this interdisciplinary collaboration and asking critical questions. Yeah.
Okay, thank you. Is there any question in the room? So if it's not the case, I ask the people on Zoom if someone wants to ask a question to Guido. Yeah, they are here, but I think nobody is answering. Okay, So I guess we can close the seminar now. Thank you again.
Thank you.
And I have a little gift for you. It's an umbrella because it's raining, or it will rain this afternoon. So
Yesterday we got wet.
come
Yeah.
back to the hotel in a safe way.
Okay, thank you very much. I appreciate it.
Welcome.
It was really a pleasure. Just, you know how to find me, Guido, GERIG, whatever. So if you have follow-up questions, if you have to know something more about software publications, I would be happy to.
Okay, thank you.